Alright, we're going to get started here, you guys. For today's lecture, you should have a note sheet that was sitting by the door as you came in. There's going to be a lot of stuff to write. I tried to put what I felt was the most important on the note sheet. So you might not be able to get everything that you want to on that sheet. So I would encourage you, if you're a big note taker, you want to write a lot, have a notebook out too. I think it might be beneficial for some of you to do that. You don't have to be fumbling around with it. You also might want to have your fluid structures 1 out. So you're going to do a couple of those. Alright, so, guys, we need to get going here. We got a lot to get through today. We almost didn't get through everything last hour, so you guys can't talk when I ask you to get something out. It's just gotta be ready to go right away. A lot of people are asking, how do we know how to do, when there's, I mean, people are talking about Mr. when there's a double bond, or when there's we're gonna learn all about all that today. So, please hold off on questions and all that stuff. We're gonna learn how to do the bond dipoles today. We're gonna learn how to do electronegativity today with all kinds of stuff today. Okay? Just want to point out, ladies and gentlemen, this is the last time I'm going to ask, otherwise I'm just going to ask people to start leaving the class. Okay? You need to be quiet. Thank you. Fluid Structures 1 is going to be due tomorrow. Fluid Structures 2 is going to be due on Friday. You're getting Fluid Structures 2 today. There's going to be quite a few problems on both of these, so we can get a lot of practice. Tomorrow, in small group, it's going to be completely dedicated to questions and working through some of those together. Also, on Friday before the quiz, we're going to take about 15 to 20 minutes to go over some review, since we kind of crunched this down into one little unit. So we're going to have a little bit of extra time. Okay. There is a fluid structures quiz review. We are not going to hand it to you and force you to do that, because you have enough to do with 1 and 2 here. For those of you that would like extra practice before the quiz, I would print out that review. It's going to be a similar format to your quiz. So maybe on Thursday night, you want to know how you're going to do in that quiz, you print out that review, do it. That's going to give you a good gauge of where you're at for the quiz.
Answer key's below it. There's a link with the answers online for the quiz.
Yeah. There's an answer key below it. I didn't post the answer key on Canvas. I will do that too. Okay, so it'll be on Canvas or the website, both places. Okay. Today, we're going to be talking about bonding still. This is not on your note sheet. Just want to touch briefly on the difference between a covalent bond and an ionic bond. We already learned about what a covalent bond was on Monday. Covalent bond is when there's a sharing of electrons happening. So if you look up here, you see these 2 electrons are being shared between both atoms, and now that's allowing both atoms to have a full octet or to become stable. The other type of bond, this is called an ionic bond. So there's not always going to be a sharing of electrons. What can happen sometimes is that one atom is going to basically steal electrons away from the other atom. So you see up here, this electron right here, it's literally been taken from this atom and moved to the atom over here. So what does that tell you about the charge? Well, now we have an atom that's positively charged and an atom that's negatively charged. If you guys know anything about this stuff, opposites attract. So that attraction is what's going to hold these 2 atoms together. This example up here would be like lithium, because lithium has literally 3 electrons, and chlorine. So maybe like lithium's donating this to chlorine or fluorine. That's specifically up here. Down here is just a picture of how we represent this. So anytime you see a picture like this, so a Lewis structure with bonds drawn in, that's a covalent bond. It means that they're sharing electrons there. So you'll never write an ionic bond like that. When you see an ionic bond here, you see that this chlorine has an extra electron, it's negatively charged. Sodium has, well, basically no valence electrons now. It still has 8 technically, but it's lost its 1 valence electron, and it's positively charged, so they stick together. Okay, we're going to use that when we talk about electronegativity. So this is where you're going to figure out how to do that, the electronegativity difference in the bond dipole part of your sheet. Now, the pictures up here are representing different atoms. Basically what electronegativity is, it's when an atom pulls electrons away from another atom in a bond. So I would write this down. Now we're going to draw out basically 3 different types of sharing of electrons here. This first type, what we're showing here, what I've drawn on there, and you're going to draw this on your sheet too, it's representing, that circle that I've just drawn is representing basically the valence electron cloud of that atom. So we're saying that the atom on the left, that's its valence electron cloud. This is the ones on its right. They're overlapping equally here. It's important to realize that, so that they have an equal overlap. So I would draw these in on the picture so you can see that equal overlap. What we're trying to show here is that's an equal sharing of electrons between these two. So one doesn't really have more than the other. This is like if Colin and Seth are best buddies and they go over to, I don't know, Seth's house and they're going to play with their toys and they share the toys equally. No, neither one of them is stronger than the other one. They like to share those toys equally. That's kind of what's happening. Okay, this type of bond is called a non-polar covalent bond. That non-polar is telling us that one of the atoms is not really hogging the electrons. Alright, second type here, you're going to draw one bigger circle, so this should be bigger in size than your other ones. And then you're going to draw one smaller circle, so a smaller electron cloud. This is an unequal sharing of electrons. So this is like, now I come to the picture, I go over to Seth's house, I'm a bully, I'm a jerk, so I steal like 4 of Seth's toys, but I'm a little bit nice, so I just let him play with one still in the corner. I don't know if Seth will let that happen. Basically, one of the atoms is hogging all the electrons, even though they're still sharing a little bit here. And we call this a polar covalent bond. When you hear poles, guys, you usually think of what? North-south, you think of opposites. So when you think of this here, when you hear polar, make sure you're thinking that one of the ends is going to be a little bit negatively charged and one's going to be slightly positively charged. So the one that's doing the hogging of the electrons, it doesn't have a full-on negative charge, but it's going to be slightly more negatively charged because it has the electrons closer to it, if that makes sense. So this one's going to be slightly positively charged because it has the electrons around it less of the time. In the last example, we're going to have one big circle. The other one is not going to get a circle at all. And this is when electrons are not shared at all. So now I went over and I took Seth's last toy, and now he's a little cool. And I have all of them around me as a kid. So that's basically what's happening here. As you can see that this negatively charged one, it now has all the electrons. It's taken all the valence electrons away from the positively charged. So you can see, remember last year we talked about the size of the atom when this happens. So the size of this one is much greater than the positively charged one. Why? It's because it's taken those electrons away. This is what happens in an ionic bond. Now, we have a way to determine what type of bond it is based on values. So what we can do is we're going to use this electronegativity chart. So this basically, it tells us how much an atom is going to pull electrons away from other atoms. So if you notice, fluorine is at the top. So fluorine is going to be the most likely element to steal electrons from other things. And if you look at the bottom, potassium is going to be the least likely to steal electrons from other things. What we do is we take the difference between two atoms, and that's going to tell us whether it's an ionic, a polar, or a nonpolar covalent bond. If that value is between 0 and 0.4, it's a nonpolar covalent bond. So I would write, you need to write these values on there. You're going to need this when you do your sheet. If the values are between 0.5 and 1.7, it is a polar covalent bond. And finally, if it's equal to or greater than 1.8, it will be an ionic bond. We're going to do an example of electronegativity difference and a bond dipole for oxygen and sulfur. This is number 8 on your sheet on Lewis structures 1. So take a look at Lewis structures 1. I'm drawing this in the bottom here. Our example is oxygen and sulfur. So what we need to do is we need to find oxygen and sulfur on our electronegativity chart. So I find oxygen, it's up here, it's 3.5. I'm going to find sulfur. It's right there, it's 2.5. What I'm going to do is I'm going to take the bigger minus the smaller, always. So I take 3.5 minus 2.5. So you write this in. Electronegativity difference. This goes in the electronegativity difference part, number 8. You write 3.5 minus 2.5. And the answer that you're going to get is 1.0. So then, what you need to do is tell me what type of bond is this, guys? Right, polar covalent. You just write polar in there. So it's a polar covalent. You can't really see it at the bottom, but it says it there. The next picture over, what you need to do is write and draw out what's called a bond dipole. What this means is we're basically showing which of the two is pulling the electrons towards it. So if you look at these two, which one's going to pull the electrons? Oxygen, right? It's more electronegative. So the one that's more electronegative is going to pull the electrons. You're going to draw an arrow with a line like this towards the one that's more electronegative. So make sure you don't draw this on a line. Make a new line with the arrow just right above it like this, just like I drew. And then what I need you to also write is there's a partial positive charge by the sulfur. That's what that symbol means. And a partial negative charge by the oxygen. So think about it like if oxygen's pulling some of the electrons, it's going to be a little bit more negatively charged. And if sulfur's losing some of the electrons, so it's not completely losing the electrons, they're still sharing them, it's going to be partially positively charged. Make sense? Okay, I want to also do, and I'm not going to write this one down. Number 5. So number 5 is carbon and hydrogen. So if we take a look up here, and I'm not going to write this one out, you guys can write it as you follow along with me right now, but you see carbon equals 2.5. So first you got to find carbon, it's 2.5. Now we got to find hydrogen before we can subtract and find it. It's 2.1. So we always take the bigger minus the smaller. So if we take 2.5 minus 2.1, it's going to be, what's the value? 0.4. What type of bond is that? It's non-polar covalent. Okay, if it's non-polar covalent, do you think that we're going to have this situation? Is one going to pull electrons from the other? No. So what do you think we're going to do with the bond dipole? Nothing. That's the answer. So if you get a non-polar covalent, you do not draw a bond dipolar. You just leave it as is. So you put it just like that. It's done. Okay, sweet. All right, we're gonna move on to some Lewis structures now, and we're going to do number 10 on your sheet together. Well, after we talk about finding central atoms. I forgot this last hour too. It's okay. Okay. Okay, I just want to talk about finding the central atom really briefly. You guys, if you flip your sheet over, this information is on the back of your sheet. I'm not going to linger on this very long. I just want to point a couple things out to you. So if you look, it says helpful guidelines in arranging atoms in Lewis structures. That's just a fancy way for us to say, telling you what the central atom is. The very first rule, it says hydrogen and halogen atoms usually bond to only one other atom in a molecule. So if you look at chlorine, it's a halogen. All the halogens look like that when we draw out their Lewis structure. You look at hydrogen, how many spots do each of those have to bond? One. That's why they're usually going to be on the outside of an atom. It's not going to be a central atom because they're not going to be able to bond to more than one thing. That's pretty self-explanatory. Next one. The atom with the smallest electronegativity is often the central atom. And the third thing on here says when a molecule contains more atoms of one element than the others, these atoms often surround the central atom. Now it doesn't say every time, it's just often with the last one. But the second one, the atom with the smallest electronegativity is often the central atom. So you look up here, if we're looking at P and Cl. So here's phosphorus, here's chlorine. Now, electronegativity goes up to the right like this. It gets more electronegative as we move that way. So you see that phosphorus is actually less electronegative than chlorine. That's why it's going to be the central atom in this problem. And there's also more chlorines than phosphorus. So there's a couple ways you can tell here. For the CO2, you look at carbon and oxygen. Carbon is less electronegative, and there's more oxygens than carbon. That's just a couple rules on figuring that out. Now, we're going to go on to number 10 on your sheet right now. So we're going to do a couple Lewis structure examples. The one that we're going to do is BCl3. Always, 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 the first thing we need to do is figure out how many valence electrons do we have to work with here. So, we got to look at boron. How many valence electrons does boron have? 3. And then we look at chlorine. How many does chlorine have? 7 times 3, so it's 21. Plus 3, we had 24 valence electrons to work with here. So no matter what, our picture cannot exceed 24 valence electrons because we literally don't have more than that to work with. We have to stick with 24 here. So we know we have 24 electrons. Okay, we're going to draw this out. Sorry, we're going to put boron here in the middle. And we're going to draw 3 bonds off the boron. What I want to point out on the left here is these octet exceptions. And this isn't on your note sheet. You might want to write this down somewhere. But there's going to be 2 exceptions to the octet. And what I mean is that there's 2, so you can write this down on the note sheet if you have space somewhere, or you can write this down on the notebook. It doesn't matter. Just find a little spot to jot this in. So the octet exceptions are the top 2 in group 13 here. So boron and aluminum. And the exception is that they are both stable with only 6 electrons. So they do not need a full octet. So now you have hydrogen needs 2. Boron and aluminum needs 6. Everything else is going to be 8. It's just 2 exceptions to the rule. You got it. You just have to. So both stable is 6. So I put B in the middle here. I'm going to put chlorine, chlorine, chlorine on the outsides. So what do I need to do next? Always fill octets. So I need to make sure that I have an electron around chlorine enough to get that octet full. So now there's 2, 4, 6, 8 around that chlorine. Now there's 2, 4, 6, 8 around this chlorine. And finally there's 2, 4, 6, 8 around that chlorine. So now we check. Do we have the same number of valence electrons as the start? So we count 1, 2, 3, 4, 5, 6. Bond counts as 2, so it's 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24. So I have the valence electrons the same as the start. I shouldn't have to check my octets again since I just filled them, right? I probably should have did that right the first time. But if we look, I have 1, 2, 3, 4, 5, 6, 7, 8 around this chlorine. 1, 2, 3, 4, 5, 6, 7, 8 around that chlorine. 1, 2, 3, 4, 5, 6, 7, 8 around this chlorine. Around boron, I have 1, 2, 3, 4, 5, 6. So is boron good? Yes, because it's an exception. So it's full. So I'm good to go. Next one I'm going to do is number 10. I believe. Flip it over once. No, Li. Number 13. It's number 13. Now don't write anything right now. Please put your pencils down. I want to walk through this one with you guys. I just want to show you a few things. I'll tell you when to start writing. So we're going to do CO. First thing we need to do, always, find how many electrons we have to work with. So we look up at the periodic table. We see carbon has how many valence electrons? 4. Oxygen has 6. So we have 10 electrons to work with here. Now I'm going to draw my picture out. I have oxygen and carbon. There's an electron here and an electron here. They're bonded together. Once I have that bond, I don't need the electrons anymore. Okay? Bond them together. Now, I'm going to put all the valence electrons that each one has. I'm just going to draw the Lewis structure. So carbon will have one more here, here, and here. So now I can use all 4 carbon's valence electrons. I'll add these ones for oxygen. So now I have 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5, and 6 here. Okay. Carbon has 4. So I have the same valence electrons as my start here, right? So I can check that off. What about my octets? Are my octets full right now? No, so this isn't good, is it? That's not complete. So what I need to do, I need to find a way to fill the octets of carbon and oxygen without adding more electrons. I cannot add more electrons here because that's just, they literally don't have that many to work with. So I need to work somehow with these 10 electrons to be able to figure out, okay, what's going on here, to be able to get their octets full. So what I might do here, I might take 1 electron from carbon down here, 1 electron from oxygen right here, and I can throw a bond in there. So now they're sharing those 2 electrons. This would be called a double bond here. So I have 2 bonds there. Now, is it good right now? Oxygen has 2, 4, 6, 8. Oxygen's good. What about carbon? 2, 4, 6. So I'm not good, right? It's not stable. It's not done yet. Okay, so let's see if we can figure out a way to get carbon full. So we pull this electron in from carbon. Let's pull this one in from oxygen. We make that bond there. Now look what happens. I have 2, 4, 6, 7, and 2, 4, 6, 7, 8, 9. So that's not going to work either, is it? Okay, so I gotta try something else. So maybe oxygen's generous. So maybe oxygen will share these 2 electrons with carbon here. It's going to make a bond there. Now, count them up. Is this good? 2, 4, 6, 8. 2, 4, 6, 8. Are my octets full? Do I have the same number of valence electrons that I started with? Let's look. I got 2, 4, 6, 8, 10. Well, that's what I said I needed right here, right? So I'm good. That right now would be called a triple bond. Does anybody want to go through guess and check like this when they're doing these? Especially when you have to do like 30 of them. You gonna want to do that? No. So now you can write in on your sheet this next part. We have a method for you guys to find these extra bonds. When I say finding extra bonds, I mean to find that double bond or to find that single bond in a Lewis dot structure. I first learned this method from Mr. Gussie last year, and I was like, where have you been all my life? Like, seriously, I didn't learn this in high school or college. I don't know how I did it back then. I don't know how I ever survived from it, because this is so much easier than anything else that I've ever been taught. It's called the TV method, okay? So what you should be doing right now, you write a T equals and B equals off to the side somewhere on your sheet there, and you're going to want to write in these steps. Now, this is somewhat on the back of your sheet too, a little bit more in depth there, but it's going to help you to write these out, okay? So, the very first step is to draw a Lewis structure with all single bonds and full octets. So, we're going to focus on the one we just did again. So, carbon monoxide. So I write down here, I had to draw a single bond between C and O. And then I'm going to draw it out like it has full octets. Now I know I just said that you can't exceed the number of valence electrons it has, but we're not finished right now. Okay, this is just part of the process here. So we're gonna draw that out there just like this. And what we're gonna do, we're gonna count how many electrons are there. That's gonna be what we put for T. So we look down here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 electrons. So we're going to put that in for our T. Very good. Okay. Number 2. We're going to write in the total number of valence electrons the molecule should have. And it says in parentheses, this is from the periodic table. So this is going to be where you put the number of valence electrons that we have to work with. So that's going to go in your V. So we kind of already did this, you guys. What's V going to be for this one? We add 4 plus 6, 10. We have V equals 10. The third step, you're going to subtract V from T. And it says every 2 extra electrons is 1 extra bond. That number is going to go underneath here. So you're subtracting V from T. T minus V is going to be plus 4 here. It's important that you write plus 4. We're not going to get into negatives for the Lewis structures portion, but next unit, when we get to molecular geometry, we're going to have negative values for T and V, so you need to make sure you write plus 4 there. So it says that every 2 extra electrons is 1 extra bond. So if I'm at plus 4, that means I have 2 extra bonds. Now that would be that double and that triple bond that we had. The very last thing I do is I draw the new structure, including my extra bonds. So now I redraw the entire structure. So what I do is I take and I put C, single bond to O. That's the first bond. Now I need 2 extra bonds. So there's my first extra bond. There's my second extra bond. That's called a triple bond. What's the last step I need to do then? Anybody? We always call it filling octets. So we got to fill that octet of carbon and oxygen. And all that's going to be is to put 2 electrons on the outside here. So you're putting a lone pair outside C and a lone pair outside O. Now I can check to make sure that all my stuff cancels out here. So I'm going to look. Are my valence electrons the same as the star? I look, I go 1, 2, 3, 4, sorry, 2, 4, 6, 7, 8, 9, 10. That's good, right? That's what we want. That should always match our V. Are my octets full? I'm going to go 2, 4, 6, 7, 8, 2, 4, 6, 7, 8. So my octets are good. See how this works? It's a lot nicer than just guessing and checking.